In this question it says, suppose a pair of compounds A and B can react in two different ways. So for reaction 1 we have A plus B yields C, and for reaction 2 we have A plus B yields D. The following facts are known about the two reactions. Reaction 1 is exothermic and reaction 2 is endothermic. And the other fact is, if a reaction vessel is charged with A and B, then at first D is produced faster than C. Use these facts to sketch a qualitative reaction energy diagram for both reactions. So we have some information, and we want reaction energy diagrams or reaction coordinate diagrams for each of the two reactions. So what I'm going to do is I'm going to put reaction 1 here and reaction 2 over here. And we're going to end up with reaction coordinate diagrams. So I'm going to draw two axes, sketches. So this is the reaction coordinate. You can think of this as progress of the reaction. So this is the reaction coordinate. And here we have energy in kilojoules per mole. And here we have energy in kilojoules per mole. So in both cases, the y-axis is energy, the x-axis is reaction coordinate or reaction progress I've seen before on some books. So this is just essentially, it's not exactly time, but it's how the reaction is going. So let's look at this situation. So the first thing is we need to draw A and B in both cases. Well, A and B should be at the same energy for both reaction 1 and reaction 2 because A and B are the same, right? So they're the same, so they have the same energy in kilojoules per mole. Now we need to use the information to find where C and D are. So that's the first thing we're going to do, simply because this is given first, and plus it's easier to do this first. So it says reaction 1 is exothermic, reaction 2 is endothermic. We don't know how exothermic or endothermic, but if reaction 1 is exothermic, we know that C must be lower in energy, I'm going to put it here, than A and B. For energy to be released, C has to be lower in energy. Said another way, for the reaction to be exothermic, C has to be lower in energy on the y-axis than A and B. If reaction 2, which produces D, is endothermic, D has to be higher in energy than A and B. How much higher, we don't know, but we do know that it has to be higher in energy. Next, it says if a vessel is charged, filled with A and B, then at first D is produced faster than C. Well, if D is produced faster than C, it means the activation energy must be lower. We'll assume these things are at the same temperature and concentration, the A and B, and it's actually the same flask, so they must be at the same temperature and concentration. So therefore, we know that the number of collisions is the same. But if D is produced faster, it means the number of effective collisions, the ones with enough activation energy in order to overcome and form the product, have enough energy. So what we can say is the activation energy must be relatively low for D. So remember that this is the activation energy. And I should note, you probably don't need to put this on the diagram. I'm just showing you that this is the activation energy. If C is produced slower, it means that the activation energy for C must be higher. So the absolute value here between A and B in the transition state has to be smaller for reaction 2 than for reaction 1. So if you look at now a reaction coordinate diagram in these two cases, what you can see is it tells us two things. One, it tells us whether it's endothermic or exothermic, or it tells us about the relative stability of the products. One could say C is more stable than D because it's lower in energy. And we know it must be lower because this one was exothermic and this one was endothermic. It also tells us about the rate of the reaction. The reaction with the lower activation energy is going to occur faster than the reaction with the higher activation energy. This makes reaction coordinate diagrams extremely useful. It tells us about the relative stability of products, and it tells us about the relative rate at which they are formed.